So let's look at an example. Let's say you have a bottle of water, drinking water, sit on the kitchen counter where the ambient temperature, the room temperature is 72 degrees. So the data, this is what's given in this example. Okay, T sub 0 equals 72 degrees Fahrenheit, and that will be the room temperature. It's not the ambient temperature in this case, because what happened is we take this bottle of water and we put it in the refrigerator and we let it sit over there to cool off. So in this case, the ambient temperature will be the temperature in the refrigerator, where let's say the temperature setting in the refrigerator is 44 degrees Fahrenheit. So this will be the refrigerator temperature. One more piece of information given to us, that the temperature after 30 minutes is 61 degrees Fahrenheit. So this will be the temperature after 30 minutes. What do we want to find? Really, we need to find three things. First, we want to find the temperature. Now, let's do two things. Let's find what is T after 1 hour. So T after of 60. That will be the first thing. And then we need to find the time such that, so this is lowercase t, such that the temperature of the bottle T of T is dropped down to, let's say, 50 degrees Fahrenheit. Just to look at the process, okay, visually, what we see, if we graph a possible, a sketch of a possible function, T of T over time, so the horizontal axis is the time in minutes, and the vertical is the temperature in Fahrenheit. We start at 72 degrees, and we end up at 44 degrees, which is the temperature of the refrigerator, right? Initially, we have a rapid drop in temperature, like so, and then it slowed down and cooling off, and then eventually will stabilize to at 44 degrees. If we leave the water long enough in the refrigerator, it will pick up the ambient temperature. Are we doing okay so far? I mean, this is the layout of the problem. And now we are ready to go. The first thing we want to do, of course, is find the solution to the differential equation. Let's just first come up with some values for the different components here. For instance, because
what exactly is the ambient temperature?
It's the temperature of the inside the refrigerator. It's the temperature of the environment. You take the bottle of water from the kitchen counter. So the temperature of the water was 72 degrees, and now you put in the refrigerator where the temperature of the environment is held constant at 44 degrees, and now the bottle is cooling off. So that's T sub S. Okay. So, because we have cooling, then we're going to say that we're good? Good. So, because we have K, which is the relative cooling rate, equals T prime over delta T, right? And it's translated to Y prime over Y. The solution for Y will be Y equals Y sub 0 e to the power of kt. And our task is to find all the different components, k, y sub 0, and so on. So let's see, what is y sub 0? Let's start with that. By definition, y sub 0 will be T sub 0 minus T sub s. T sub 0 is the initial temperature, which was 42 degrees. T sub s is the temperature of the environment inside the refrigerator, which is 44 degrees. So the difference, I believe, to be 28 degrees Fahrenheit. Okay? So the other thing we know is that the temperature after 30 degrees was, after 30 minutes, was 61 degrees. So Y after 30 minutes will be T after 30 minutes minus T sub S, or 61 minus 44, and that will be 17 degrees. So we have Y of 30, we have Y sub 0. I'll go ahead and plug it here. So Y after 30 minutes, so let's say T equals 30 minutes, Y after 30 minutes will be Y sub 0 e to the power of k times 30. And time now to replace the values, as we do when we solve exponential function. Y of 30 is 17, Y sub 0 is 28, and it's equals to e to the power of 30k. So this one I can skip a step or two. We'll divide both sides by 28. So we have at this point we have 17 over 28 equals, I'll do it without skipping. And then we apply the natural log, and we have natural log of 17 over 28 equal 30k, and therefore k itself will be 1 over 30 natural log of 17 over 28, like so. And you plug it in the calculator, and you come up with a value, and if you calculate it correctly, I like to keep it like that. I don't want to introduce rounding errors, but it will be negative 0.01663. Let's say this is up to 5 decimal points. So that's why it's rounded, but it's rounded up to 5 decimal points. So now at this point I have k, and therefore I know that y is a function of the time will be y sub 0, which is 28, e to the power of kt. And I'm ready to solve the first part. So all of this was a warm-up. In the first part, recall, we need to find out what is the temperature after 60 minutes. So T equals 60 minutes. And therefore, what is Y after 60 minutes? Y of 60 equals 28 e to the power of k times 60. Again, use the calculator, and I came up with but rounded to 1 decimal point is 10.3 degrees Fahrenheit. What does it mean? What happened here? Well, what is y of 60? Remember, y is the difference, right? I want to find t of 60, so y of 60 is t at 60 minus the ambient temperature, T sub S. So T at 60 minutes will be Y at 60 minutes plus the ambient temperature. So it will be 10.3 plus the 44 degrees, the temperature of the refrigerator. So we end up having 54.3 degrees. Let's see if it makes sense. Okay? Remember the data. The first data that we were given was that after 30 minutes, the temperature was after 30 minutes, temperature was 61 degrees. So for the first 30 minutes, the temperature dropped from 72 to 61, a drop of 11 degrees. On the other hand, for the next 30 minutes, from 30 to 60, the temperature dropped from 61 degrees to 54.3 degrees, approximately 7 degrees, or exactly 6.7 degrees. It does make sense. It fits this scenario that we have here. The first 30 minutes, we have a very sharp drop, and then the next 30 minutes, we have less drop. And then the next 30 minutes, we have even less drop. Okay, so far, it passed the smell test. It smelled like roses. Now, the other part is we want to know the time where the temperature equals, was it 50 degrees. So T of T equals 50 degrees Fahrenheit. We want to find the time. Again, I'm going to convert it. If T of T equals 50, Y of T equals T of T minus T sub S, or 50 minus 44. So this is something to keep in mind. You always have to play between T and Y. So we're looking at Y equals 6 degrees Fahrenheit, and we set up the equation 6 equals 28 times e to the power of k t, where k is known. And now we'll divide by 68 and apply the natural log. So the natural log of 6 over 28 equals kt, and therefore t equals 1 over k, the natural log of 6 over 28. Okay? And k, I know what it is, and I calculate it. And again, I've done that, so I end up having 92.6 minutes. So let's see. Here we're looking at drop from 72 to 50 degrees. Okay, we drop. It took an hour to drop from 72 to 54 degrees. And now, between 60 and 92, another 30 minutes, the temperature drop was only 4.3 degrees. Let's just summarize this so you see the bigger picture. Okay, if I set up a table T in minute and T of T in degree Fahrenheit, we end up having the following. We have the first two we know. At 0, we have 72 degrees, and at 30, we have 61 degrees. This is given to us. What we end up calculating, at 60, we end up having 54.3, and at 92.6, we end up 50 degrees. So this was calculated. And the point is, it's consistent with the exponential decay function that we started here. So this is an example for Newton, application of the Newton's cooling law.